I want to do a two-part video on what is the deal with the square root of 3. I've done this presentation before, and so I've mocked it up a little bit from what I had before. So why do we need to know the square root of 3, right? What is it convenient for? Power calculations, current calculations, voltage calculations, TTRs on transformers, relay testing, meter testing, or even PTs, right? So sine, cosine, tangent, and the Pythagorean theorem. If you understand these right here, then it's just playing with the geometry and you can figure out that it is the square root of 3, okay? So how do you apply those sines, cosines, and tangent? This triangle right here, okay? This is how you're going to apply them. I'm not going to sit here and give you a high school algebra lesson. This is basic trigonometry. And so, and you know, a little, maybe not basic geometry, a little bit more advanced geometry, but not terrible, okay? So if you don't understand this, there's plenty of resources online to go ahead and figure that out. But sine, cosine, tangent, you need to know how to use these. All right. So what is the next thing that we need to learn for this? Well, it's going to be phasor diagrams. We need to understand what a phasor diagram is. That's how we're going to represent it. Okay. So whenever you talk to someone, especially an engineer, if you want to get them really riled up, just tell them that phasors aren't real. Okay. Are they? Well, no, they're technically a graphical representation of what the system is doing, okay? Is a sine wave real? No, it's technically a graphical representation of what the system is doing. If you look right here at this center, what's actually happening in this wire right here is the current is going back and forth, okay? And so how are we going to represent that with some kind of piece of paper, right? We're going to draw that like it's going slowly in one direction, and it gets to the full stop, and then it comes back down and it goes the other direction until it goes to a full stop, and so that we turn it into a sine wave. Okay, that's all it is. So this is a single phase representation. We're going to go over the three phase, but I just want you to see that this is why we use sine waves and why we use vector diagrams. They're just representations of what the system is really doing. Okay. So how do we convert this? As the current starts going more and more in one direction, we're gonna, you know, as the current goes up and up and up, right? That's what it's doing in the wire. We take this and we directly correlate that to a phasor diagram. Okay, that's what we're doing. So that's what these phasor diagrams are. And so when you look at a phasor diagram, if I were to have A phase here, right? And then B phase is going to start right here. It's going to come about right here. It's going to come over. But right here, it's going to come down. It's going to go right here, right? So that means that B phase should be about right here. And that's how we do this, okay? And where is C phase? Well, C phase C phase, if we were to plot this on here, right? C phase is going to start at the next 120-degree increment, right? And it's going to go up like this. And then we can draw it back down like this, and we can come up to about right here. And if you look, that C phase will line directly right up with 120. Okay. And so is it 120 degrees? No, that's just a representation in time. What we're saying is that this entire cycle right here is from here to here on A phase is 16 milliseconds. Okay, 16.6 milliseconds. So that's one cycle. That's one rotation that we're going to represent. Where would C phase be if it was in a rotation? Well, at the same time, at that point in time, it would be 120 degrees apart, you know? So that's what we're saying. Out of 360 degrees on a circle, you could just say it's 1/3 behind it too. You could say 1/3 of 16 is roughly like 5 point something. It's 5 milliseconds behind A phase. That's true as well, okay? So that's what these representations are. Here's a three-phase example, okay? So on the three-phase example, it's all the same stuff's happening, and we just do it 3 times and overlap it. And if you look, this magnetic field, it's still just a single-phase DC magnetic field right here in the center, okay? But the thing is, it's just going to rotate through each one individually and create these sine waves, okay? So one comes first, then the next one, then the next one, then it goes back to the first one, right? And so it just keeps rotating. And that's why we use vector diagrams, because it's a very simple way to represent them. But it's just a diagram. It's not real. It's something that we made up to make it easier for us to understand, okay? So this is what the three-phase diagram looks like right here, okay? It does get a little bit more complicated than this if you want to go ahead and say that you have fault currents or some poor wave shapes and stuff like that. So we're not going to go into any of that stuff. But this is a three-phase diagram, and this is what I was trying to show earlier, where each of them are in their phase cycle. Okay. Now, the thing about this is if you were to trace this over time, and this is time, right? So going this direction, this is time. The x-axis is time, and the y-axis up and down right here is your amplitude of your voltage, okay, or current. So time is this way, going left and right. And if we were to plot this through time, what you would see as each section, the amplitudes change. And so if you were really looking at a live phasor diagram, it wouldn't look like this at all. It would be looking like this, but spinning 60 times a second, okay? And that's not helpful to us. So what do? Okay, this is what I'm showing here on the left-hand side. It would be rotating at 60 times a second. That's not valuable to us if it just looks like a blur. So what do? We take this and we lock a phase right here to 0 degrees. And we just call that 0 degrees. We know in our minds it's spinning at 60 hertz, okay? But we're going to say that it's at 60 degrees. And if we see any angle change between these here or this here, right, then we know that B phase or C phase is starting to slow down or speed up relative to A phase, okay? That's all we're looking at there. And that's exactly the same way you would look at a synchronoscope as well. This last one I want to point out down here, this is a phasor diagram, because technically, engineering wise, you would say these are vectors, right? Because they have a magnitude. How long this thing is a magnitude right here, okay? And then they also have a direction, some angle theta, okay? And all vectors have a magnitude and a direction, but when you assign an electrical quantity to it, it becomes a phasor. And so that's why they're called phasor diagrams, okay? Some people like to call them vector diagrams. That's because they're stuck in the mechanical engineering world or they're just untrained. But it's technically a phasor diagram when you start looking at electrical quantities, okay? So right here is what it would look like with the finished product, right, of a phasor diagram. And so when you go to your power meters, this is what you would see, hopefully. You would see something that looks just like this. This would also be 120 degrees here, okay? Nothing special here. But this is a phasor diagram. A phase voltage is locked at 120 volts at an angle of 0 degrees. Okay, this is how your relays and your power meters operate with it. So with this, we'll go ahead and take this information of phasor diagrams and our trigonometry, and we're going to calculate the distance from here to here. Okay.